In my career, I've gotten involved in the patent system. A lot of companies like to use patents kind of like trading cards. So I've gotten a lot of patents. And I think that's one of the reasons they gave me the job at the university from industry, because in the university they look at the papers you published. If you're in industry, they look at patents that you got. All of these patents have to do with the industries that I was in at the time, which is mostly data storage. Some of them are kind of dumb. Some of them I don't think are really that innovative, and yet we still got patents. But having gone through that process so many times and dealt with so many lawyers, I know probably quite a bit about it. So if you want to learn about the patent system, I can tell you a few things. Things I worked on. This is my career highlight. This is the Storage Tech 4400 robotic tape cartridge handling system. It was manufactured just about 6 miles down the road at a company called Storage Technology, which was a spin-off of IBM, and it's a big machine that robotically handles tape cartridges, and I was the main servo engineer on that, and it's been in the movies a few times, including Arnold Schwarzenegger's movie Eraser and Harrison Ford in Patriot Games. In the original cut of Patriot Games, they had a long scene with this thing in the movie with Harrison Ford in the foreground. So we enjoyed that. I found out later it was paid advertisement, and it was stripped from some versions. It was, let's see, it starts out with the British monarch being attacked by terrorists, and Harrison Ford goes in. It's actually a really excellent movie, by the way. So that's the closest I've gotten to being in Hollywood. But that machine, when it moves, that's me making it move pretty much every step of the way. Inside that machine, you have this fairly complicated mechanical assembly. It's got, so those are shells where tape cartridges were held, and this is a robotic arm. It extends, it grips, it rotates, it has a camera. We did all this a long time ago, like 20 plus years ago. And it worked pretty well, and I learned some hard lessons on that I will teach you about that are still germane to everything we do here. And there's a shot from a screen capture from a movie. That's some famous movie star. I don't know which one it is, but this is what it looked like in the movie. It was pretty cool. I could see the thing moving around for about 60 seconds, and then when it finally went to cut the screen, or cut the scene, the robot rotated around, and you could see the word Storage Tech there, indicating that was obviously product placement, but we had like 60 to 90 seconds in the movie, which was cool. I've also worked on this machine, which is a real fun machine to work on. This is a dental X-ray computed tomography machine. A person sits in this chair right here, and we shoot X-rays through their head for 30 seconds, which is a long exposure of X-ray. And the X-ray is not a point, it's what we call a cone beam. So in doing that, the patient gets a significant dose of X-rays, 430 microsieverts, as I remember. Does anybody, probably nobody has a clue as to how much radiation that is. I mean, what's a microsievert? You know what a mile is, you know what a pound is, maybe, if you're English. Here's 30 seconds in that chair. The way to think about that is, well, we all know that there's cosmic radiation coming in from the sky all the time that you can't avoid. So I'd like to use that as a good comparison. Say, well, if you sat in that chair for 30 seconds, is that equivalent to being outside in Colorado for 40 seconds? A year? How much extra radiation is that? Anybody want to hazard a guess? I'll make you hazard a guess. Jeet, how many days equivalent radiation do you think that machine gives you in 30 seconds? A year? More like 2 months. Not a bad guess, though. What do you get for that? So you're getting a couple of months extra radiation. And by the way, cosmic rays are double here than they are at sea level. This is the X-ray tube. Excuse me, it's a bad picture. That's not that's the X-ray tube. This is the X-ray receiver. It's basically a large format digital X-ray camera. And if you expose somebody like that for 30 seconds, you rotate it around their head like this. So the camera's here, and it's really an array of amorphous silicon photodiodes. That's what it is. But it's large. It's as large as a person's head. You can get a three-dimensional X-ray, and then through the magic of software, you can reconstruct every bone in the person's head to less than a millimeter accuracy, which doctors need when they want to place dental implants. And Jeff, do you know what a dental implant is?
Dental implant, like a filling or crown, something like that? Or?
Similar. Anybody else? What's a dental implant? You're all too young to know. If you completely lose a tooth, nowadays they can put a new tooth in. And they do that by using a titanium screw. And that was actually an accidental discovery. It was accidentally discovered that bone will grow and adhere to titanium. That was discovered a number of years ago, and since your jaw has bone in it, they drill a hole, put a screw in there, and the bone will actually adhere to it, and you have a new tooth. I think it costs about $3,000, even though it doesn't take that long for the doctor to do. This scan here, if you go to a scanning center, they'll charge you $300 for that. The doctor will have a great picture of your jaw, and he'll look at it, and he'll say, yeah, there's enough bone there to do it. Here's a picture of the large format digital camera. So these are made in Salt Lake City, Utah. I went there by Varian Corporation. It's a big, complicated assembly line. They cost, at the time we were looking at $25,000 for one of these. And after seeing what they had to do to make them, I said, oh, okay, I kind of understand. But this is all active imaging area. And it's not crystalline silicon, it's amorphous silicon, which is not as good as crystalline silicon, but it's relatively immune to X-rays. If you put crystalline silicon on there, you'd get a nice sharp picture, and the thing would degrade after a relatively short period of time. And for a while here, right here in Boulder, Colorado, down by Spider on Walnut Street, I had my own personal X-ray machine. I could X-ray anything I wanted. It was really cool. Yeah, very interesting to look at cameras or cell phones or something. Here's an example of the picture you get, except you don't get the color. So it's a false color image. But we can put that picture up and show that any angle you want, any slice thickness you want. You can all do that with the data that comes back from that digital imager. So it was a pretty cool machine. And of course, I've worked on a bunch of other things. These are the ones that I found pictures for quickly. So let's talk a little bit more about this. Remember this slide? Remember the pictures of the philosophers? Anybody know who the philosophers were? Can you name one of them? Abhinav. Aristotle? Aristotle? Probably. I'm not sure myself. Socrates, Plato, Aristotle, I think. Truthiness. I just wanted to say this because I can't talk to you all semester long and everything I say is strictly true, because it would just take too long to say everything. I can't be exact in every statement I make. So take everything you hear with a grain of salt. And some people here will know what that phrase means. Some will not. It's an American colloquialism. It means a certain amount of skepticism. Or put this way, another favorite quote of mine, Lou Reed. He said this 20, 25 years ago. Don't believe anything you hear. Only believe half of what you see. And this was really before Photoshop got popular.
He really looked like that. He's scary.
Oh, yeah. He's a Long Islander, isn't he? I think so. Textbook. I didn't talk about the textbooks last time, so this is available for free download from the CU library. One of the reasons I chose it, the other reason I chose it is all about sensors, and it's relatively new. It's October 2015. When I was an undergraduate and I was taking medieval history for my elective, we had a professor, I think I might quote him later, who said that textbooks are intellectual baby food. And I laughed at the time, and I didn't know what he meant, but after looking at the textbooks and then comparing that to the app notes and white papers that are written by companies that actually build these parts, I kind of see what he's saying. Textbooks are a little dumbed down, but we'll use this as a reference material. You don't have to pay for it anyway. Besides that textbook, there's a couple things that come out from companies like Analog Devices and Texas Instruments. These guys really know what the heck they're talking about. And they don't have any axe to grind, like they don't want to just impress you with how smart they are. They just want to get the information across. And I find that these books are actually really very good, and it's always enlightening for me to read through those. And I always go, shoot, I didn't know that. That's really, you'll like them. I think they're very good. Oh, and here's a quote from Professor Harris. Textbooks are intellectual baby food. There's definitely a grain of truth in that. So I think the best sources of information are the industry-issued application notes. There's a lot of them out there. There's YouTube videos. You can download these left and right. I have personally downloaded, I think, well over 500 of these. Haven't read every one of them, but almost all of them are really good. I throw out a few here and there. Magazine articles like you find in the magazines like Electronic Design News or Electronics, they're generally not as good. Sometimes they're very good, but they're generally not quite as good. Some of the online videos, well, that's real hit and miss. I've seen some that are gems, especially the ones where the guy takes the time to put in animation. I think that really explains things very well. A lot of them are of poor quality. So the problem you have here is everything that I tell you, all of that information, you can go look it up. It'll take you forever because there's so much out there and you're going to have to sort through it. So I spent the last year sorting through a lot of this stuff and try and feed you the stuff that I think is good. So let's talk a little bit about technology. Enough about the class, enough about me. I'd like to get into technology. And this is a very important subject, analog versus digital ground. Yes, it is true. You do need different grounds for analog and digital, and the next picture will, I think, explain everything in a flash to you. It's a little more complicated than that next picture will show, but it will get the point across, and it will be the most important point. So you look at a board, and you might see A ground and B ground, and you put your multimeter on there, and you check them, and it's the same voltage because you're checking DC. There's a very big difference between direct current and fast pulses. Fast pulses excite the inductance that's inherent in every wire and every trace. You've got capacitance between there. The AC, the alternating current story, the dynamic story is very, very different than the DC. So don't be fooled that analog and digital ground are connected together. Yes, they are at DC. The important thing to remember is all wires, everybody thinks have finite resistance, of course, but they also have inductance. You might think of a wire, a straight wire, how could that possibly have inductance? Because we've all seen inductors are coils, right? And you coil them up, and then these magnetic fields add. That's how you get an inductor. But no, even a straight wire has inductance. And that means if you try and put a fast signal through it, there'll be a voltage drop there. And that's why every chip on the board has a bypass capacitor on it. Because those voltage drops, if they had to go over a long distance to supply current to that chip for 10 nanoseconds or 1 nanosecond, the voltage would drop. So you have a local source of electrons right at the chip. That's your bypass capacitor. Here's the picture that I think will explain everything very simply. Picture's worth 1,000 words. This is a good example. Let's suppose you had a board that had some analog circuits and some digital circuits, and you wired it like this. This is bad. See, it's in red. I like color coding. This is bad, and this is why it's bad. Because every time a digital circuit draws current, it's going to flow through that outer loop, and they're sharing that outer loop with the analog circuit. So you will have voltage drops and peaks here on the analog circuit ground. This guy might draw half a milliamp, but he draws it really fast. And so the voltage here, if you put it on your oscilloscope, you'll see spikes and such in there. You don't want that. All you have to do is do this. This is the difference between the analog and the digital ground. The analog circuits are generally not putting in these really fast spikes. They have their own ground. This guy can do it all day long, and he is much more immune to those spikes. That's the basics of analog and digital ground. The paper goes into quite a bit more. It goes into some confusing points, even to me, about separating analog digital ground, even on an A to D converter. And I never noticed that before, but you'll find A to D converters that have separate analog and digital grounds. And what I find really confusing is sometimes, in some cases, you said connect the A to D converter's digital ground to the analog ground, which that really threw me, and I had to read the paragraph a couple of times, and I'm still not sure I understand it. But this is the basic idea. This is really, if you know nothing else about why you separate analog and digital grounds, this is why you do it. If you put a multimeter on here and measure from here to any other point in there, unless you have a very, very accurate multimeter, it's going to be 0 ohms all the way through. It's DC 0 ohms. It's not AC 0 ohms. I found a number, I think it was in the same paper, a 22-gauge wire, and you can find online engineering handbooks. I downloaded one. They'll tell you what these numbers are. A 22-gauge wire has about 20 nanohenries per inch. Anybody here know what an inch is who's not a U.S. citizen? It's about this far, 2.54 centimeters. Just kidding. I know you know what an inch is. 22-gauge wire, just an inch of it has 20 nanohenries of inductance. It's not coiled up. It's just straight. It has 22 nanohenries of inductance. So if you had a signal with a slew rate of 10 milliamps per nanosecond, that's actually significant. And remember I talked about needing to have a feel for the numbers? You need to have a name tag. And after you do that, I'm going to call on you. Where's that magic marker? Anybody have that? That's why I brought two. There you go. Pass that down to this gentleman. Thank you. If you had a signal that had 10 milliamps per nanosecond, which is not insignificant, you develop 200 millivolts on there. I didn't see anybody jump up and go, oh, 200 millivolts? Or I didn't see anybody go, 200 millivolts. As engineers, you need to have a feel for the numbers. Is 200 millivolts a lot or not? So I just did this quick little calculation. Is 200 millivolts a lot? Well, it depends on what you're doing. If you have a 16-bit A to D converter, we've all heard about 16-bit A to D converters. Every CD player, 16-bit. And the input's 0 to 5 volts, which is a very reasonable number. Well, you're breaking 5 volts into 65,530 ash. Thank you. You have to feel for the numbers. That many parts. And so each bit is, what's that, 76 microvolts per bit. And so 200 millivolts is, you're up by 2,600 counts. People all the time, they tell me, oh yeah, I got 16-bit A to D converter here. Yeah, but what's your real accuracy? It's nowhere near that. You're just kidding yourself. Or in this case, in my previous job, is 200 millivolts a lot? Depends on what you're doing. That Illumina X-ray CT machine charges the X-ray tube up to literally 120,000 volts. And you wouldn't believe how simple that circuit is. I got the diagram for the tube and looked at it and I said, must be something wrong here. It's got to be more than that. You know what's inside that tube? Some capacitors and some diodes that can literally support several thousand, 4,000 or 5,000 volts a piece. I didn't know you could buy such things. It's actually just a fairly simple circuit. Capacitors and diodes, it's a charge pump. I believe it was like the 1939 Nobel Prize, and somebody figured out you could jack up voltages that high and make particle accelerators. Well, one of my jobs was to make sure that the thing is charged up to 120,000 volts. How do you think you do that with a microprocessor that's between 0 and 5 volts? Somehow you have to interface it to something that's 120,000 volts. I was shocked when I heard that. Not literally, fortunately. How would you possibly do that? Anybody want to hazard a guess? Terran? How would you measure 120,000 volts, somehow interface that to a microprocessor that'll blow up if you put more than 5.5 on any pin?
Step up transformer.
It's DC, can't do it. What was that? Shekhar?
Yeah. I just told step down.
You're going to say step down. Well, believe it, do you know?
I don't know. I was thinking like just a multiplier.
Yep.
Yeah.
It's just a voltage. I could not believe it. There you have a resistor in there that's this long, and it's like 20 mega ohm, which means with my Fluke DVM, which is a very good DVM, I can't even measure it. So I'm not even sure how you measure it. It just used a voltage divider. I was so surprised. So that system, which pumps X-rays through somebody's head, amazingly simple. It's just each component in there has amazing specifications. A capacitor that can support 5,000 volts, a 20 mega ohm resistor, diodes that have a back voltage on them of a couple of thousand apiece. Just go to DigiKey. You do it right now, Mauser, any of those sites, and look up diodes and see if you can find a diode that you can put more than a couple of hundred volts on. Actually, I don't know if DigiKey sells that. It might be a real specialty item. But that's how it's done. An amazingly simple circuit. Okay, now let's talk about actuators. Fun topic for me because I've done a lot of different actuators. They all have interesting and different characteristics. So I just pulled this off the internet as an example of an interesting actuator. By that I simply mean something that moves under microcontroller command. And I sometimes use the term microcontroller. I sometimes use the term microprocessor. Prithvi? What is the difference between a microcontroller and a microprocessor? Loudly.
Microcontrollers got more resources on it. It's got A to D converters.
Yeah, I'll buy that. It's just, you know, in the old days when transistors cost a lot more money than they do now, a microprocessor just had computing capabilities, could add, subtract, couldn't multiply and divide. It had a little bit of memory, and that was about it. Microcontrollers, you got a lot more stuff on. This PSOC board, to me, this is a microcontroller on steroids. Because not only does it have all these other resources, but you can wire those resources up arbitrarily. And I hope I have time to get to that today and show you, because this is, to me, this is like the coolest board I've ever used. And I've used a lot of different boards, and this thing is really fun because it gives you such freedom of action. If you screw up, you just erase it and do it again. Anybody remember that old toy called Etch-a-Sketch? No? Really? There used to be an old toy that you had a couple of knobs, and it would actually just scrape some silver paint off of a screen, and you could draw a picture, X, Y. And when you were done, if you didn't like your picture, you just took it up and down, shook it, and the paint or powder would redeposit on the screen. This is like an Etch-a-Sketch. You can just build whatever you want in there, and if you don't like it, you just erase it and do it again. That's what makes it so powerful. I think eventually the flash memory in here burns out, but I think you have about 100,000 tries. So you're not going to run into that. I think I mentioned last week, you know, what are the various types of actuators? There's step motor, DC motor, brushless DC motor, piezoelectric devices. AC motors are generally not used as servo devices. They're harder to control, but they are controllable, especially with the power of the electronics we have today. I left out something here, thermal. Actually was shown a long time ago, right here in Boulder, Colorado. A salesman came by and said, I got a new gadget for you, Jim. It was basically a little piece of wire. When you heated it, you know, it would change diameter, or excuse me, change length. And he says, you got a use for that? I said, no, but I'll think about it. It was very interesting. All these others, like I said last time, they're electromagnets. They're just different configurations of electromagnets. That's really where you get the power from. This mechanism over here, I've never used this one, but I see what they're doing. So you have a motor here, and probably on the back side of the motor here is some sort of encoder that tells you what the position of the motor is. See, this has extra piece that hangs on there. There's a gear going down here, and then you have a lead screw over here, and there's all sorts of problems with this. There's all sorts of advantages. First of all, you get the tremendous gear ratio advantage. You get a lot of power out of this linear stroke. The downside, especially from a control system standpoint, remember that's what I did for a long time, is that there'll be backlash in those gears. There'll be a little bit of this. If the gears are really tight and they don't rattle at all, when I say go this way, it goes this way. When I say go that way, it goes that way. If they rattle a little bit, there's that little interval time where it might do something else, and that really screws up the control system, and it's really hard to actually really hard to fix that. I've never really seen a good explanation. I'll tell you ways to mitigate that, but if you have backlash in your control loop, it's always a problem. The other thing that really screws up the control loop is another non-linearity. Cyan? What else would be a problem in a mechanism that would screw up a control loop? Any idea? A non-linearity. Common, very common. No, I asked him.
Yeah, so like you have something like where you have to rotate for a certain degree, and like if it's fixed angular displacement, or if it's fixed that you cannot rotate to a definite point.
You're close. I was thinking stiction. Anybody heard that term, stiction? We all know what friction is, right? Rub your hand together, there's a little bit of resistance, that's friction. If you look at the force you have to apply between two objects to get them moving, if it starts to move with any arbitrary small amount of force, then there's no stiction. But in practice, almost everything has a certain amount of stiction, which means you put two things together and you apply force to one to make it to move. Nothing happens. And you increase the force, at some point it breaks away. And that really screws up a PID control system. Don't ask me how I know that. We'll talk more about that later. That's one of the things that never taught me in college, but I know it because I dealt with it. Yes, sir?
Is that the same thing as adhesion?
Yes. That we really use the term stiction. It means static friction. The stiction goes away. And when that thing breaks free, that's the problem. That's a nonlinear event. PID control systems are all built around the idea of a linear system that you're controlling. And by a linear system, I mean it's a basic position. If you double the input force, you double the output force. That's not true for stiction. I can increase the input force up to some level. Nothing happens. Then all of a sudden it starts to move. Then it becomes a linear system, but it just made that sudden transition from nonlinear to linear system. PID control systems do not handle nonlinearities. You have to basically do tricks in the software to fix that. And that's what I got good at, and I found it surprisingly effective, but hard to justify mathematically with any rigor, but I know that it works. And we'll talk more about that later. What are some of the issues you get into with actuators? And this is just a short list. Yes, sir?
Is that this word stiction that you mentioned, is that an acronym for limiting static friction?
Say that again? So is it?
Is that an acronym for limiting static friction?
It's yes. Static friction, stiction. That's why we use it, yes. Actuator issues. So maybe some of these are obvious and maybe some aren't. But the big one is you get a lot of current. Your microprocessor operates on milliamps, and your actuator operates on maybe a couple amps, maybe tens of amps, maybe hundreds of amps. Question? No? So you've got a board here, like this one. Somehow you have to interface it to a motor over here. That motor might be 50 amps. And 50 amps, you run it through even a pretty fat wire, even at DC, and you'll get a pretty significant voltage drop. And so you try to measure what that current is. There's all sorts of issues with that. We'll talk about the electronics that are involved. Control loop stability, I just talked about. That's mostly a problem due to those two things, backlash and stiction. If you have a system with backlash and stiction, beware. It's hard to control. Best thing to do is to try and eliminate the backlash and stiction. If you can't, then you're going to have to get a little bit tricky with software. And I'll show you how to do that because I've done it. Overheating, there's another problem. The electronics that drive the actuator, pushing a lot of current. They're going to get hot. You have sensors on here. You have a microprocessor on there. Those sensors will, all sensors drift with temperature, right? So if they start getting hot, then you start getting less accurate. Another important point to keep in mind is that all control systems are designed to minimize the error as indicated by the sensors. Notice I didn't say designed to minimize the error. It just, because they don't know what the error really is. All they know is what the sensor told them. And therein lies the problem. If your sensor tells you the error is 0, that's all you know, and the error is not actually 0. And as a friend of mine pointed out recently, a good example is in an older car, there's a thing called a mass airflow sensor in the intake that measures the air going into the engine. And I didn't know this, but they get dirty. And they start to read incorrectly. And he says, oh yeah, you could buy cleaner. He says, clean mine, the car runs a heck of a lot better. I didn't know that. The good example of you only know what the sensors are telling you. Well, besides heat from all that power, you've got danger from high voltages, and therein lies another problem. There are standards in the industry for how far apart the traces have to be. It's based on the voltages involved. You'll have leakage currents on the board. So that fiberglass, pretty good insulator, right? Put your $200 flute BVM on there, and it's reading more than 10 mega ohms. But in practice, you put 200-300 volts on there, you might get a little bit of current going across. That current might be microamps, but that might be enough to really screw up some of the other boards. So just mixing those, not just the high currents, but also the high voltages on the same board, well, one has to be careful. I talked about IR drops. Fault isolation and diagnostics. Now, that's another interesting thing. I've dealt with robots that, they move things around, and when they don't work, I get a phone call from somebody, and he says, well, what happened here? And I said, well, you know, they kind of describe what happened. And I said, well, can you send me a trace from the code? And he said, yeah, I could do that. And then we got into this little game. He'd just go do something. He would introduce a fault, send me the trace, and I had to figure it out. And I quickly realized, oh, there's more to this than I thought. And if you architect your system cleverly, you should be able to tell when somebody's just simply disconnected the motor. Can they tell that? Or maybe they just dropped the power. Or maybe they jammed the motor. And that actually happened to me at Exabyte Corporation, which is just a few miles from here. I had somebody walk into my office and say, "No, Jim, your servo's broken." I said, "It is?" "Yeah." I said, "Look at this thing. It just failed on me." And I go, "Really?" And I looked at the trace and I said, I think you jammed it. I think there's something jammed in here." And he said, nah. I said, "Give it to me." And 5 minutes later, I walked back in his office and I went, and I put that screw on the board. Because I could tell from my trace that we had applied power to the motor, that the voltage was still there, the motor didn't move. That could mean the output stage is blown, but I didn't think it was blown because I didn't see any obvious physical damage there. So my conclusion was something jammed it. And it was real easy to jam that mechanism because it was tiny, and the motors have magnets, and they attract little screws. You drop a little screw in there, eventually it finds its way into the motor and jams the thing. So I was able to figure that out just by looking at software. So how do we interface a microcontroller to an actuator? Well, here's our microcontroller. 0 to 5 volts, operates on a couple of milliamps. There it is. Over here we have a power amplifier. Somehow we go from some signal here to give me tens of amperes over here, a motor that might be driving a pretty heavy load, some sort of sensor. How do you do that divide? Anybody done this before? Taken mechatronics or anything? Not that hard, actually. I'll explain how this is done, but this is the important thing to remember. Back over here, it's pretty small voltages, pretty small currents, big voltages, big currents. You can do this, by the way, with this board. I have a picture for you in a second. So here's one good way to actually do that. The microprocessor, or a microprocessor just knows about numbers, right? It can write numbers, it can calculate numbers, it writes a number out. You have to design circuitry that takes that number and does something with it. If you write to a digital to analog converter, well, now you've got some analog voltage. So the microprocessor can write a number to an analog the circuitry will create an analog voltage from that. You can build a circuit, actually with PSOC, which I have built, and I've demonstrated it here last semester. You can build a circuit that takes that analog voltage and forces the current in the motor to be proportional to that number. That's really not too hard to do. You measure the current in the motor, and with a comparator, you compare it to the voltage properly scaled that you wrote to it, and if it's too much, well, you shut the voltage off to the motor. And if it's too little, you turn the voltage on to the motor. That's called a bang-bang servo system. That actually works fine. Now your microprocessor has a way to control the current in the motor. And you probably, maybe you don't know, DC motors, brushless DC motors, the current in the motor is directly proportional to a very important characteristic of the motor. Gabrielle. The current in a DC motor is proportional to
Innovation?
No, but close. Torque. The current in the motor is proportional to torque. And the integral of torque, or torque divided by inertia, calculus anybody? Torque divided by inertia? Velocity? Excuse me, acceleration. Torque divided by inertia is acceleration. Integrate once to get velocity, integrate again to get position. And there's where, so you were just missing a couple of integrals and a divide by the inertia, but you're right. So if you design a circuit, and I'll show it to you actually in the next slide, that takes a number that the microprocessor wrote and forces the current in the motor to be proportional to that number, now you have control of the torque of the motor. And if you have control of the torque of the motor, the mathematics to go from torque to acceleration is, well, you just divide by the inertia. If you have gears in the system, anything that's geared down to the motor, that gets multiplied by the square of the gear ratio. Integrate that once, and you've got your velocity. Integrate it again, you got position. So the mathematics to go from current control to position of the motor is straightforward, linear, understandable, and that's why we do it. And here's how you do it with a PSOC. So sorry, it's a little bit busy. We got pretty big monitors here, but I'll just show you how I did this. This is an actual working circuit. I built this for somebody because, actually, I built it for myself when I started working with this board, and I thought, gee, I bet I could do this pretty quick, and I did. So here's our brushless DC motor. It has 3 coils. On each coil is power transistor. You got an upper and a lower power transistor. I turn those power transistors on and off with this chip, this component that's inside the PSOC chip. It's called a lookup table. It's just digital. And actually, there's a little bit of a voltage translation between here because you really need a gate driver to do this. But this lookup table just turns these transistors on and off to make the motor spin. The current in the motor always flows from VDD through one of these transistors like this guy, through one of these coils, through the other coil, only 2 out of 3 coils active at any time, through this lower transistor. So if I turn this guy on and this guy on, and I have a fixed voltage here, the current starts to rise. There's an inductive rise time. That time, compared to how fast a microprocessor works, is forever and a day. The microprocessor can sit there going, da, 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 I'm waiting for the current to come up, blah, blah, blah. It flows through here, and my circuit makes it go to ground through a small resistor, 0.3 ohm resistor. And just like that 120,000 volt X-ray machine, if you want to measure current, you could do it magnetically, but you can also just do it through a resistor. The voltage on a resistor is just proportional to the current. And since it's a small resistor, it's not a lot of voltage. But the voltage here tells me what the current in the motor is. So I compare that using a comparator to a number that I wrote from my microprocessor. Let's say I wrote 100, and the voltage here is 2 volts. I can amplify this small voltage here any way I want, but if the current is too high, this comparator changes state. If it's too low, it changes state the other way. I feed that signal back to my lookup table. So when the current gets too high, I just turn these transistors off, and the current starts to decay. A little more complicated than that, but it starts to decay. And when it decays a little bit too far, maybe I wait a certain amount of time, or maybe I allow it to go down by some percentage, I'll turn it back on. I will chop the voltage. I will turn those transistors on and off at a rapid rate, and the current will do this. It will rise, and it will fall. That's a switching power supply. That's all you need. This is like the simplest one you could possibly design, which is why I designed it, but it also works. It works so well that I used it in class last semester to demonstrate PID control loop and how you can increase and decrease damping and what happens when you have a little bit of stiction and so on. It actually works great. That's all done in a PSOC. These components here, these things that have a little bit of color on them, those are all actual parts that are inside this chip. The stuff that's in blue is external to the chip because in integrated electronics, you can't put power transistors. These guys have to be able to handle amps. We can't do that inside a microprocessor chip. And we can't build a brushless DC motor inside the microprocessor chip. So blue means it's external. To make a complete PID control system, I need some feedback. I need to see what the motor's doing. This motor happened to have an optical encoder on the shaft in the back. It gives me 2 pulse trains that tell me what the position of the motor is. Those 2 pulse trains just run into here, and there's actually a standard way to decode that, basically a very simple state machine called a motor position controller. And out here, or I can read this, and I get a number that tells me what the position of the motor is. So now I know where the motor is, and I can control the torque. So in software, it's PID. You can actually make it 1 line of code. Especially if you use a floating point, you don't have to do all this bounds checking to make sure you overflow your number and so on. So the software does the proportional integral derivative control. It takes this position and says, is that the position I want to be at? If not, you have some number that you just invented. I want to be at position 100. I read the number from here. That number might be 120. So I say, okay, I'm plus 20 off of where I wanted to be. How fast am I going? Well, what was my position a millisecond ago compared to my position now? With this same number, I could just use time and get velocity, and I can also integrate errors. So the software does the proportional integral derivative control. This circuit turns on the power transistors, and that's how it's done. We did it years ago, and it actually works remarkably well. There's a lot of little issues there, but that's the general idea. So now you know how to build a closed-loop PID control system, and you know that if you have backlash or if you have stiction, that it may not work right. Questions? Comments? The power amplifier that I use, a set of transistors here, I lent that board to some graduate student last semester, swore to return it, and I haven't seen it yet. So if he gives it back to me, I'll hook it up to this with a motor, and we can actually watch it work. If not, I've got a lot of pictures of it working, but I lost my power amplifier. The power amplifier, by the way, just plugs in right here, wire it over to a motor, hook up a big power supply, and it works. Yes, sir?
So instead of this, we can use a motor driver, and the motor driver is connected to the piece of ILP, and then use a brushless DC motor to control the motor.
Not instead of this. That's what this is.
Okay.
That's what this is. This is a motor driver. It's the diagram simplifies a little bit. You're probably thinking of a motor driver that maybe does the PID. You can go to hobby shops and buy a servo motor.
Yeah.
Okay? And the servo motor maybe doesn't work just like this, but it has a signal where instead of you writing a number to this guy and getting control of the current, you might say, I just want you to move to this position. And that thing will somehow move to that position. There's more than one way to do that. It could be a stepper motor. Yes, sir?
Yeah. Does it have a variable resistor in the background attached to the shaft of it so it knows position?
Not a variable resistor, and the reason we don't use a variable resistor is it wears out. We use generally optical encoders or now Hall encoder. I don't have it here. We have some motors with Hall encoders on them. You want something that's non-contact, that's not going to wear out. But a variable resistor would definitely work. As a matter of fact, I did one, a linear one, where I had a variable resistor. That's used in sound tables, PV electronics in, was it Louisiana or something? They have these, they make rock and roll power amplifiers and stuff. It's a very cool place. And they have these sliders that control the volume and probably other properties of all the different channels out there. There's so many of them that they wanted some way to memorize the position. So they have a linear resistor in there. Microprocessor memorizes the position. Guy comes in the morning, flips the switch, and they all move to that position. Yeah, I don't know if you saw it in my resume there, but the last couple of years of my career, I was a field engineer for Arrow Electronics. So instead of designing my own stuff, Arrow Electronics would send me around and I'd talk to customers, mostly about this. So how might you use that in your system? And that was a very interesting job because I got to see all these different things. Like I got to go to PV, the place that makes amplifiers and soundboards and so on. Got to see all sorts of interesting stuff. Okay, let's talk a minute about, watch my time here, development tools. So when I took this job and I asked people about development tools used at CU, first thing I heard is everybody's really sick of Arduino by the time they get to be a senior. And I'd never used an Arduino, but I looked at it and I said, yeah, okay, that's a nice tool, but it's kind of simple-minded, even the new ones. There are a lot of cool things out there. I mean, Raspberry Pi is amazingly high computing power. I think it's, 1.2 gigahertz clock now, a lot of memory and so on. But it's not something that's good for interfacing sensors because it doesn't have any analog stuff on it. Beagle bone, I think, is a similar sort of thing with a little bit less computing power. But this guy is a great tool for interfacing sensors because you can make your own sensor interface and see if it works well. As a matter of fact, I will try to design some of these labs where I give you the freedom to do it different ways, and we'll have a little contest to see who gets the most accurate results. Because there's some simple things that you need to know about that can give you that extra couple of % of accuracy. And I think I said it before. It's not really that hard to hook up a sensor to a microprocessor. Hobbyists do it every day. What's hard is accurate and fast. If you just want 8-bit accuracy and you don't care about fast, any idiot can do it. If you need something that's really accurate, and a lot of jobs out there, they want really high accuracy. They want microns. They want to split microns into micromicrons. Or they need it really, really fast. That's where it becomes a lot more difficult. That's where you need to have a degree in electrical engineering. You're not a hobbyist at that point. So I saw this. I thought this was really cool, and it would be a great tool for this course. There's a nice picture of it. I've held it up a number of times. It has all these interesting parts on it. So the PSOC 5 LP chip is just that, and then they just added all this other stuff on, just toys for you to play with, right? So if you need to control a motor, and the motor needs to have a couple of amps, they give you this breadboard here, and that's one of the things we'll do. It just takes a power transistor, like an IRF 540, for instance, and a few other passive components, like you can't integrate big capacitors into a chip like that. So you put capacitors externally, the high current stuff externally, and you can actually control a brushless DC motor. We did that experiment last year. Other parts on here, well, there's capacitive sensing, which is just basically a pattern on the printed circuit board. And when you touch this, that creates a small change capacitance on the order of a few puff. That this trace is wired over to some of the input pins there, and it has specialized circuitry that is designed to be able to detect very small changes in capacitance. This thing right here is a slider. It's actually kind of a series of wedge-shaped buttons that when you touch it, you're actually touching more than one button, and you can see how much more over one than you are the other, so you can slide your finger back and forth. You actually make a slider. So capacitive buttons like this have, a huge advantage, and they don't wear out. They're much more complicated to implement than a physical button, but they don't wear out, and they're really cheap. The electronics to do it, transistors are really small. We get billions of them on the chip now, so they're not expensive. But to actually make it work is tricky business. But once you do, you have something that's really reliable, like this. And I don't think anybody's seen their cell phone screen wear out, right? What else is on here? There's a variable resistor potentiometer. Maybe we'll do a lab about that because that's like the simplest possible thing that you could interface to a microprocessor. So there's just like a 10K ohm resistor, and it goes over here somewhere, and you can hook it up and maybe run it into the A to D converter and print out on a display that you have a certain voltage there. You can power this board just by hooking up your USB cable to that one in the corner. Don't hook up to this one over here. That's a USB interface that you can program from here, but this is the one that gives the board power in the corner. I had that power amplifier. It just hooked right up to the analog port. And all of these pins here are pins that you can program and control and do whatever you want. You want a blinking LED, you can hook it up to, port 5, bit 1, whatever that is. Quick intro to that. So I think I mentioned this last week. Why do this? It's real mixed signal. I haven't seen none of the boards really mixed signal. A lot of microcontrollers, they'll have an A to D or a D to A on them, but they're fixed. You can't do anything with it. You might be able to change the number of bits by configuration register, make it an 8-bit A to D or a 10-bit A to D. With this, you get to change the wires. That's the difference. You get to wire it up. And once you start throwing wires around, the number of iterations or different things you do is pretty much infinite. I also think it's very quick to learn. And what I really like is hardware and software in one tool. And I remember back in 1978 in a job interview in Data General in Massachusetts, the boss looked at my resume and says, well, Jim, you know, the reason I brought you in here is because you put down on your resume that you do hardware and software. And I go, yes, that's right, because anything you do with a servo system or mechanical system, you got to do both. Right? You have to understand how the microcontroller works. You have to understand a little bit about the analog circuitry. You have to be able to build a power amplifier, and then you have to tie that together with software. If you can't do all of those things, then you can't really build the whole system. And if you can only build one part of the system, you're not going to do a very good job because you won't understand what the trade-offs are. Let's see if I can do what I was not able to do last week, which is bring up PSOC Creator. Okay, there it is. This is the same picture. This is the actual project, by the way, that brushless DC motor. If you start this software, how many have downloaded the software? Anybody? Comments? Good, bad, indifferent? Took too long to download? Pretty good? Okay. There's a lot of great software out there. That's the big difference, by the way, between when I got out of college and what you guys have now. Every time I get on the internet and I look at something new, I go, holy cow, what a really cool piece of software. And it's free. It's unbelievable. Especially filter design software. I just discovered a new program that, Filter Pro. Has anybody seen that? You want to design an op-amp active filter, an analog? I took courses in that. I spent many hours late at night going through equations with what I thought was the cool tool, the calculator at the time. Now you just, you fill in a few boxes and it will show you exactly what the circuit is, give you a bill of materials, tell you what parts to buy, high pass, low pass, band pass, Chebyshev, amazing stuff out there. This is an amazing piece of software. So I don't have a lot of time here. Oh, I got 15 minutes. Okay, that's enough. So part of my last job was I would go out and preach this, the benefits of this to customers that salesmen would find for me. And one of the things I would tell those customers, and I think I mentioned this last time, is if you're an electrical engineer and you know a thing or two about electronics, I can show you how to use this whole thing in 15 minutes. You can be productive with this in 15 minutes. That's a big difference between a lot of the tools that are out there. There's some really great tools out there, like Quartus for designing FPGAs. I said, oh, gosh, I want to design an FPGA, too. So I put Quartus on my machine, and I started playing around with it. And the first thing it did, it wanted me to, go into the BIOS and delete some security feature, and I was not willing to do that. And I realized that's an awfully clumsy program. That's a long learning curve. What did I say before? What's your most precious resource? It's time, right? You got the knowledge. You got the facilities here. Parts are cheap. Software is cheap. It's really just a matter of time. How late do you want to stay up? You can do anything you want. So I'm very fussy about, if it takes me a long time to learn and it's not intuitive, I don't want to use it. This is a great tool. Let me show you how it starts. When it starts, this schematic page, it'll look just like this, except this will be blank. They put some other notes in there, maybe some news from the company. But like every integrated design environment I've ever used, it always pretty much starts like this. You say File, New, Project. And in this case, the software works with this board, but it also works with many other boards. And so you have to tell it which one you're using. And for a PSOC 5 LP, I'd go over here and say target device is this family. And since I was a field engineer, I happen to know the words CY8C58AXI-LP035. That's the chip that's on this board. All you have to do is get your eyeglasses out, or my generation, let's get your magnifying glasses out in bright light. We can read that number and just put it in there. I think you guys might be able to read that without that, if you have good eyesight. You say next, and start with an empty schematic. And you can use it asks you, where do you want to put this? Actually, I probably don't want to put it there. I'll just put it in my documents. PSOC Creator Projects, how about that? That works. You can give the project a name if you want, totally optional. I'll just leave it a design to you. I'll say finish, and bang, you're ready to design something. And the reason I brought in my portable digital oscilloscope today is because I wanted to prove to you that we can actually design something. If I have a cable for this, This box is in here? Yes. Okay. So this is my challenge. Oh, and by the way, notice in the white area, we threw a few parts on here. We have a power transistor, so you can control a motor. And we have this little white thing, thermistor, you measure temperature. And we have a little light-sensitive resistor, which apparently is really big in India, because all the Indian students seem to know about LDRs. I don't use them much over here. They're slow, cheap. They work, they detect light. Bypass capacitor. I was surprised at how many people don't understand the importance of bypass capacitors, but we gave you one. And then 3 op-amp circuits. And the reason we give you 3 op-amp circuits is because undergraduate, they teach you about the ideal op-amp. We're going to teach about real op-amps. These are 3 different op-amps. They're not all the same, and I think maybe that'll be our first lab next week is you'll get out an oscilloscope and a signal generator, and you'll prove to yourself, you'll compare these 3 op-amps and the op-amp that you get in here in terms of frequency response and voltage range and a few other things, and satisfy yourself, oh yeah, these are definitely different. Because I could tell you that till I'm blue in the face. But if you've actually gotten there with a signal generator and done it and looked at it and written it up, you'll remember that. So, here's how I build something. Over here on the right side, they call it the component catalog. This is your parts list. These are the parts that you have available. This is a much smaller list of parts than you will find in DigiKey, which probably has 5 million different electronic parts. Here you have maybe 100. But you do have 100 different parts. And you will find that you can build a lot of things with 100 different parts. If you can't do it one way, you can do it another way. Over here is just a list of all the files in the system. Generally, I just think of that. This is the software side, and this is the hardware side. This is your schematic. But it's not just schematic. It's also about writing code. Over here on this side, you will see, focus your attention on main.c. That's where you write code. You open that up, and you write code in there. That code will interact with the parts that you put on the board in any way you want it to. Let's show you how this is done. For instance, over here on the right side, I can expand any of these items. Here under digital functions, all sorts of digital functions. Counters, timers, shift registers, some stuff maybe you don't recognize, like the quadrature decoder, although that was in the schematic that I put you earlier. But I want to talk about something I just demonstrate really simply here. So we have op-amp. Look, there's 3 op-amps. They have their own op-amp. Their own op-amp is not bad. It's not super fast, but it's not a bad op-amp. They also have an op-amp that's combined with some resistors, and they call it programmable gain stage. So I'll just drag your programmable gain stage out over here and put it on the board. They give you a default name, PGA1, and it has some inputs and some outputs. For every component that you put on the board, if you mouse over it and right-click, you'll see that pop up. It's one of the things Cypress really got right here. They're very consistent. You don't have to learn 10 different rules. You just have to learn 1 or 2 rules, and you'll know how to do this for everything. You mouse over it, you get this pop-up, and you hit Configure. And now you get to adjust that particular part. So this screen is particular to that part. And what can I do with this? Well, I could set the gain, for instance, and here I'm going to set the gain to 2. Notice I even give you the chart that shows you what the frequency response is going to be if you set the gain to 2. And I'm going to switch the VREF from external to internal. Just those 2 changes. I just set the gain. I just set the VREF. I will say OK. And now look, the part's changed because the reference voltage is internal, but they're promising me that it has a gain of 2 from input to output. So let's see if that's true. So somehow I got to hook this thing to some pins. Well, pins, they work just like everything else. They're on the right side of the screen. I'll go over to the right side of the screen. I'll expand ports and pins. I'll grab an analog pin and drag it over. And notice it has a little box. You can run a wire from that little box to that box, or you can just line them up. So I'll do that. I'll just line them up. Bing. And now that's connected. Notice it changed appearance. I've connected a pin. It is that easy, folks. It is that easy. I need an output pin. I've got a problem here. It's pointed the wrong direction. They give you some tools up here. Rotate, flip. I just flip it. hook it up. Now I've created a circuit as an op-amp, gain of 2, with feedback. They give you some default names here. This is one thing that I didn't like, minor point. They called, the default name is pin 1 and pin 2, but that's not pin 1 and pin 2 on the chip. These are logical names. You can make them anything you want. Therefore, I will change the name. How do you think I do that? Same way I do everything else. I mouse over it, I right-click. There's that same pop-up. You've seen it before. Configure. Now this window is specific to things about pins. Pins on this board are not just pins, they're really little circuits interfacing to pins. And I'll change the name. I'll change it to input A. I'll change the output to output A. And I use A because input and output are reserved words in the system. Almost done. Now I have to somehow map this logical name called input A to something on here. And fortunately, Cypress has labeled everything on here. And if I look carefully, I see, for instance, P3_0 means port 3, bit 0. So somehow I have to associate input A to port 3, bit 0. And at my suggestion, after 2 years, they finally did it. They put a line element over here for pins. It used to be you had to click CYDWR, which was not intuitive, but now it is intuitive. There's pins. I go to Cypress sometimes and attend their industry panel, and I give them suggestions, which they don't always take. We go over here and say pins. I click on that, and, whoa, there's a list of pins. Oop, that's...
close the current project.
Do this one. Yeah, I accidentally opened, I left the BLDC motor project in the same workspace as Design 02, and I just opened the pins for the wrong project. So I go over here. This is, you can have, this is concept of workspace. We have multiple projects. I meant to only have this one. Notice in the upper right, there's those names. Input A, output A. I can go over here and select a port. For instance, P30, because I see it written on here. Here it's P3_0. Over here it's P3 square bracket 0, close enough. The output I'll make P31. And I'm done with that step. There's only one more thing to do, and it's, again, this is not intuitive, but in order to have a minimum power draw on the chip, all of these components that you have on your schematic over here, they start out in a power off state. The default is power off, and you have to execute one line of code to turn them on. So now we're going to get into the code, and this is what I think is really cool. This is a schematic. You're looking at hardware here. You're wiring things up. Over here on the left, if I click on main.c, now I'm writing code. Notice we have a hot list of tabs. This is like your most recently clicked on thing here, so it remembers for you what you recently clicked on. I'll do that again. Here we're making hardware. Here we're writing code. Hardware, code. It's really cool. In the code, they give you a very bare bones outline of main.c. It contains really nothing but comments and the comments tell you what to do there. So it has the name, main.c, and a loop. That's it. It really doesn't do anything. But pretty much all programs have some initialization and a loop. What we have to do, and they have one line of code here for interrupts, which they throw in automatically. That has to be the only executable line. Global interrupts, if you're using interrupts, that's the master switch. You can turn on interrupts and turn off interrupts individually, but you also need this master switch. And if you forget to throw the master switch, none of your interrupts work, so they just put it in there. You can take it out if you don't want. What do we have to do to turn on the PGA? Very simply. This is just simply a start function. I'll put it in here. It's PGA_1. It's always exactly this name. Again, something I appreciate that Cypress did. It's exactly the name. That's the default name of the part. This is the type of part. This happens to be the first instance, so it's PGA_1. Change it to anything you want. I didn't change it, so here in main.c would say PGA_1_ S TART. So the only thing that happens when the microprocessor wakes up is it enables the interrupt and executes a start function for that PGA that we put on the board right there, and he should become active. And now I'd like to test this. So I'll plug him in. That's it. Design's complete. I just plugged in the USB, and to download it, to build it and to download it, one button. If we're not using debug features, it's that button over there, or you could say build, clean and build, but that doesn't download it. This is the download button. The software is smart enough to know that if you made any changes, it will look, did he make any changes? If he did, it'll rebuild. So I'm going to press this one button, and let's see what happens if I get lucky here. Notice an output window popped up here. Kind of shows you what's going on. The software is looking at the hardware design you did, seeing if it's okay, and then it will execute the compiler, ARM compiler. It's an ARM Cortex M3, I think, microprocessor. It executes the code, and when it's done, I like this, green. Green is good, right? It confirms to you, build succeeded. Programming started, verify checksum, was successfully programmed. I pressed one button. It did all that. And so now, I need some wires to hook it up here. So if I have a signal from I need a signal, right? So this portable digital oscilloscope also includes a signal generator. And here's my portable digital oscilloscope. Comes from Pico Technology in the UK. Very nice little device, reasonably fast scope. It has a signal generator function over here. So signal is on. It is a sine wave, and I should be able to see it at this output port right here. Hold the ground on there, and let's make it a little bit larger signal. And let's give it a little bit of an offset, because I know that my microprocessor is 0 to 5 volts. But I can't go over 100 millivolts. Can I go 500 millivolts offset? No. Where's ground on this picture? Right there. The microprocessor runs 0 to 5 or 0 to 3.3, depending on how you set jumpers. Sorry, check my time here. So we're running a little bit over. So I'll do a 100 millivolt signal. Why is it overriding me here? Oh, it's smaller than I expected. It says 20 millivolts. I don't know why it's saying that. They just updated the software here. 40 kilohertz signal, right? I should be able to apply that signal to input A, and the output should be twice the amplitude, thereby demonstrating that I did actually build the circuit in that board. And I forgot that wire. We don't have, well, we can make it work. I'm supposed to have a coaxial interface here. Do you have that one? Oh, good. Okay. That's what I was looking for. I have no idea why it's only going to 20 millivolts when over here it says 100. If I make that a little bit bigger. Okay, I need more of an offset. There we go. And sweep it a little bit faster. And maybe go to 300 millivolts offset. Okay, so there we are. 0 to 60 millivolts, even though this says it's 300 peak to peak. Don't know why that is. Haven't seen that before. I'm going to take that signal. I would like to trigger on that. With this scope, I can just set my trigger there. There I have a very nice trigger. Okay, I'm going to take that signal and apply it to, I think it's P30. Notice after we built, if you look carefully here, it shows you P30. It confirms what you did there. So I will go over here and plug it into P30. And then ground everybody the same way. And I don't have a good ground wire on here. Okay, we'll use that. Signal generator in my left hand. Scope channel 0 is reading the input. Should still be there. So now the signal is being applied to the board. And then the output should show up at P31 if I've done all this correctly. So channel 2, red. And by the way, pet peeve of mine is channel 1 is always the input, channel 2 is the output, just for simplicity. If I turn on channel 2 over here and set it also to similar voltage, there's our output. Not sure about the scale here. Oh, I know why. It doesn't understand that probe 1 is a 10x probe and probe. Okay, so now they're both 10x probes. And I will set the scale the same at plus or minus 1 volt per division. And I'll set ground at exactly the same point for both for comparison. And probably have to go 2 volts per division, come off scale. There you go. Okay, so I just used PSOC and I just said I want a gain stage with a gain of 2. And I applied a signal from external source, this blue box, and I got it. And everything that I did there in the PSOC chip, dragging all of these components up, it works the same way for everything on that list to the right. It works exactly the same way. Assigning the pins, dragging the parts over, wiring them up. It all works the same way, downloading it. So you now know how to use this. You now know how to use this thing. There's a lot more to it than that, but what I just showed you unleashes more than half the power in that board. And that took maybe 20 minutes. So not too many. Try to do that quartus. See how far you get with quartus in 20 minutes. Good luck. But this guy, you now are enabled. So thanks very much. That's the end of the lecture. We'll see you here next Tuesday. Next Thursday, we're going to be at the ITLL, and we will be doing stuff with this board. Cut.